All right, so let's go ahead and get started. Since this is all that we have here, we'll go ahead and get started. Reminder, and I'll send this out in an email again, but just to remind you that we won't be meeting next week. I will record the material again like I have been and get it out to you with the link. Was everybody able to access the link okay?
I didn't even check.
Oh, you didn't even check. Were you able to access it okay, Daniel?
Link to what?
To the YouTube video that covered the lecture. Did you check?
I don't think I knew.
Okay, that's fine. Were you able to access? You couldn't access it, or you didn't check?
I didn't check.
Okay, all right. Let me pray for us, and then we'll go ahead and get started. So hopefully they'll use this as a way of that is Whitney, Derek, and Maddie as a way to go over this material. So let me pray. Father, you're so good and so gracious to us, and I thank you that you give us the ability to understand concept ideas and concept things, or difficult concepts. Father, I pray that each and every day as we have opportunity to interact with difficult ideas, Father, I pray that you would give us the grace to understand them, and by that, to understand more about your world. We ask this in the name of Jesus. Amen. So we are scheduled today to talk about entropy and its relationship with thermodynamics. And what I want to mention is that entropy, this concept, actually has a lot to do with the second law of thermodynamics, and we'll talk about that. So the slides here, and I'll send out the slides as well as the link to the video that we'll make from this. But a lot of this, in some ways, provides the missing material for why things work the way that they do in thermodynamics. So these slides are a little bit different. They're structured a little bit differently, but hopefully it'll work nicely. So first question I want to talk about is just what is entropy? Spend some time talking about what it is, how it works, and why it matters in the area of physics, although that one we'll deal more with in the next slide. So what entropy is it's basically a measure of randomness. I think this is the easiest way to think about entropy, is just as a measure of randomness. So if entropy goes up, you're more random. If entropy goes down, you are less random. But what's nice is there are ways to quantify how random a system is. And so, again, higher entropy equals more disorder. And that's an important concept to keep in mind. And it's important to also keep in mind that entropy can change. In fact, in every chemical reaction that happens, and I know this isn't chemistry, but a lot of what physics is explaining why things work in the physical universe the way that they do. In a lot of chemical reactions, entropy changes. Entropy changes as a result of that reaction. And so technically speaking, if you're going to quantify what entropy is entropy is the number of ways the materials can be arranged to produce whatever the macroscopic object is. So let's say your object is a living organism. So in order to quantify the energy or the entropy of a living organism, you're thinking about what are the number of ways in which we can take all of the materials that make up a living organism, all of the parts of that organism, and put them together in order to get the same macroscopic structure, the same living organism. And so for a living organism, would you suggest that entropy is high? That is, that there's a high level of disorder, or that entropy is low and there's a low level of disorder? Keep in mind how we quantify it. Yeah.
Probably like lower.
It's extremely low. So living organisms have extremely low entropy because there aren't a great number of ways in which you can organize all of the materials inside of a living organism and still get the same thing, right? Not just the same thing functioning the way it is, but the same thing exactly in the same way. So then the way this connects to thermodynamics is the second law of thermodynamics basically states this, that the entropy of the universe is always increasing. That is, the universe, and we've talked about that term before. Do you remember that term universe in context of thermodynamics and what it actually means? So the universe is the system and the surroundings together. So yeah, the system is whatever your reference point is, right? And the surroundings is everything else. Your universe is the system and the surroundings together. So the second law of thermodynamics states that the entropy of the universe is always increasing. And that's an important concept. It doesn't mean that you cannot decrease entropy. It's certainly not what the second law of thermodynamics means. What the second law of thermodynamics means is that the universe is always increasing in randomness. So in order for the entropy of a system to decrease, not of the universe, the entropy of the universe cannot decrease. But in order for the entropy of a system to decrease, the system must absorb energy. So if in any way you are going to decrease the randomness, that is, decrease the entropy in the system, you have to supply energy in order to do that. What does that mean as far as living organisms? What do you need a lot of to keep life functioning if you're going to constantly, if you're going to constantly be decreasing entropy to maintain that order in a living organism, you need a lot of energy to do that. You need a lot of energy input. And that's why, luckily, living organisms are open systems. Heat transfers in readily, materials transfer in and out readily. Organisms are open systems, so they allow movement of both heat and materials into and out of them, which is good because you need a ton of energy to keep entropy low and to actually decrease entropy, which oftentimes needs to happen for life to function. For instance, I'll give you a specific example. So in our bodies, we have muscles, and those muscles are made up primarily of two proteins. Those proteins are actin and myosin. Okay? This is, in some ways beyond the realm of the class, but it's a good example. And so in order to build those proteins, our bodies have to string a lot of pieces together to make those proteins. Those pieces are called amino acids. But if you're going to take two amino acids and attach them together, that is a significant decrease in entropy. Because so initially, if you have two separate amino acids, there are basically an infinite number of ways in which you can arrange those amino acids and have the same thing, right? Two separate amino acids. But once you string them together, you're now limited, right? You have less ways in which those materials can be pieced together and get your macroscopic object. And that's just something that's still microscopic, right? A protein that's only 2 amino acids long, which would be basically nothing. The shortest protein that I'm aware of in a human body is over 100 amino acids. And so you're talking about a significant decrease in randomness, a significant decrease in entropy, and it requires energy input in order to make that happen. So what does entropy mean in physics? What are we actually addressing? How are we using it? What are we doing with it? So first thing it means is that systems tend to become more disordered. This is a reason why living organisms break down. So while it's not correct to say that the second law of thermodynamics actually prohibits the system from becoming more ordered, it would be incorrect to say that. It is correct to say that because the second law of thermodynamics, systems tend to break down. They tend to become more disordered, that is, have higher entropy. Does that make sense, the distinction between those? While saying that a system can't decrease in entropy is not the same thing as saying that a system tends to increase. Okay, so the system can tend to increase all at once, and if you can input energy to decrease it, you can do that. But it eventually gets to a point where no amount of energy can overcome that tendency towards disorder, which is why living organisms break down. And not just living organisms, everything breaks down. Systems break down because they tend towards disorder. It's the reason why computer programs don't last forever, right? Or if you have data stored on some kind of a data storage device, over time it breaks down in the same way anything else breaks down, because even the pieces that are stringing together that data storage deteriorate due to the second law of thermodynamics. And so ultimately we get this equation, and this is a good one. You use it all the time in chemistry, but I think developing it in physics and actually talking about it in physics a lot of ways helps to explain the reason why heat transfers. The last couple of weeks we've been talking about heat transfer, right? Systems absorbing heat and doing work. Systems gaining in temperature as they absorb heat. But then there's the question of why? Why do they absorb heat? Why do they lose heat sometimes? What's actually fueling that? And I think a lot of ways this bringing in entropy explains a lot of that. So we have this equation here. G is what's called Gibbs free energy. And it measures spontaneity, which, what does it mean to be spontaneous?
Random.
Yeah, in some ways, there's some randomness to it.
Something that's no one is expecting.
Sure, that's maybe even a better way of thinking about it. Yeah, if you describe somebody as being spontaneous, in many ways they behave in a way that's not consistent with the norm, right? Mm-hmm. They're willing to do something that's a bit out of the box, if you will. So Gibbs free energy measures spontaneity, which is basically this question here. Will the process happen on its own? If Gibbs free energy is negative, the process is spontaneous, which means it will tend to happen on its own. Now, it may take a really long time for it to happen, but it'll happen on its own. I had a teacher one time, while they were teaching this idea of spontaneity, we're talking about like a junior high dance. And they said, like, given enough time, eventually the junior high boy will ask the junior high girl to dance, right? Mm-hmm. Given enough time. But that amount of time may be an insurmountable amount of time to actually accomplish in a single dance, right? So just because something is spontaneous does not necessarily mean that it's going to happen on the scale necessary for life. So be thinking, as we talk through these concepts, that there's something more than just whether or not it's spontaneous, okay? We'll talk about whether or not something's spontaneous, but there's something more than just whether or not it's spontaneous. H in this equation stands for enthalpy, which is the total heat contained in a system. So it's different than just the internal energy. We talked about internal energy, which is U. And so here's our internal energy that we've mentioned before when we talk about like delta U is equal to Q minus W, right? Or delta U is equal to MC delta 2 or delta T minus W, right? That we've been talking about the last couple of weeks. But enthalpy is bigger than that. It's the internal energy of the system plus the pressure times the volume. So it's the total heat contained in the system, more than just what it's holding as internal energy. U plus P times V, pressure multiplied by volume. T is temperature, which T tends to be in thermodynamics equations. And then what are we missing? We talked about what does entropy mean to physics. What's missing from what we've described so far in this equation? Entropy, right? What does that S mean? And so S is entropy. And notice in this equation, to try to determine whether or not a process is spontaneous, we're talking about the change in entropy, right? So is this process basically fueling something to become more ordered? Or is it fueling something to become less ordered? Okay. And that's a big one. That's a big one. That's a big question. And so here's another way of phrasing or demonstrating this equation without with replacing the h with u plus pv. And then if we wanted to, we can plug in what we know u equals into this equation and make it more complex. We're not going to do that. But you could, right? You could plug in what we know u to be equal to, which is q minus w, or mc delta t minus w. And you could plug that into this equation as well. But we'll leave it at this point. So again, why does it matter? Why does it matter if a process is spontaneous or not?
Because if it's not spontaneous, nothing's going to happen.
Well, if it's not spontaneous, you're going to have to input energy to make it happen. So a lot of what happens in our bodies, like stringing amino acids together into proteins, that is not spontaneous.
You have to put in work.
Right. You have to put in energy. You have to do work on the system in order to make that happen. Remember we talked about last time, like it is possible to do work on the system, but usually in our examples, we're going to talk about the system doing work on something else. System doing work on the surroundings, like water doing work on the walls of a balloon as it heats up. But it is possible to do work on the system, and it's required if the system is a reaction that is not spontaneous, like making proteins. All right, so then I have a couple of questions for you, and we'll work some problems. So what's more random, ice or liquid water? What's more random? And why?
Ice, because it could melt.
Okay. So you have to keep in mind that if you're talking about something changing, you're going to be changing entropy. So here's a question here. What's more ordered? The water molecules being locked into a crystal, which they are as ice, or the water molecules in a liquid where they're more free to move? What's more random? Yeah, water's more random. So liquid water is more random than ice, and so that process of melting is spontaneous. Entropy is going to increase. The enthalpy, the total energy in that system, is not going to change unless it also heats up, right? Mm-hmm. So like water is both ice and liquid at 32 degrees Fahrenheit, right? You talk about that's the temperature that water freezes, but at that temperature, water's both ice and liquid. And so if there's no change in temperature, you're still going to have a tendency for ice to melt because that's spontaneous. Entropy is increasing. You ever wondered why, like when you spill water, it evaporates? Because what's the temperature at which water evaporates? Do you know? It's 212 degrees Fahrenheit. So if you pour water on the concrete on a hot day, does it stay there all day? No, it doesn't. But does the concrete get to 212 degrees Fahrenheit? No, it doesn't. Why is it still turning from a liquid into a gas? Because entropy is increasing to go from a liquid to a gas, which means that's a spontaneous process. So it's going to happen even without that water having to get to 212 degrees Fahrenheit, which it won't. You're still going to have water moving towards a gaseous phase. All right, what about this one? A fully assembled car or a completely disassembled car? What's more random? Disassembled. And let's quantify it. So if you have a fully assembled car, how many ways are there to organize all of the materials and get the exact same thing? One, right? Maybe a couple, right? I mean, you could probably, if your driver's seat and your passenger seat are the same, you could probably interchange them, right? And make that still work. But there aren't many, right? There aren't many ways in which you can arrange all the materials in a car and still have the same thing. But what about just a pile of all the parts? There are a ton of ways that you could arrange that and still have it be a pile of all the parts, right? So quantifiably, that has more entropy. One of the reasons why cars tend to break down, right? Go to a junkyard and look at a car. And it doesn't take much work. You know, things rust, things just deteriorate, things break down. And the last one, This one's kind of fun. A star or a supernova? What's more random? So all of the, atoms in a star held together, constantly going through chemical reactions, or an explosion in which those atoms are strewn all about. What's more random? The supernova, right? Which is why stars, at least if they're a large enough star, they tend to turn into supernovae, okay? Because that is a spontaneous process. Entropy increases.
Can you repeat why again? Like why it would be that?
Why it would be...
Supernova has...
Yeah, so think about this. So you've got a star. Let's use our sun. So inside of the sun, you basically, what's fueling the sun and what's fueling, sunlight and that solar energy is a chemical reaction of hydrogen fusing together to become helium, right? That's what's fueling that process. And so if all of those materials are held in a very discrete space, right, in a confined space where they're able to interact with one another, that there are fewer ways in which you can arrange that and still get the same thing than having the materials just strewn all about moving through the universe, right? And so anything that's more random or more chaotic is going to tend to have higher entropy, and it's going to tend to be a spontaneous process. That makes sense? Any questions? Okay, so we're gonna do a few problems together. All right, so the first question here. If a reaction is carried out in water and has an enthalpy of 457.5 joules and a change in entropy of 4.37 joules per degree Celsius at 55.4 degrees Celsius, is it spontaneous? Okay, so first question of what do we have, or what are we given? Well, we know that H enthalpy is equal to what? Given to us by our problem. 457.5 joules. What else are we given? We're given temperature, right? Temperature is equal to what?
4.37 joules.
No, that one's entropy. Yeah. 55.4 degrees Celsius. And then finally, we have change in entropy, which is delta S, is equal to 4.37 joules per degree Celsius. And the units for entropy are important. It's not just like a constant where you just string a bunch of units together to make things cancel out, right? We've seen that before. Where have we used constants before? Maybe we haven't seen that, unless we... No, we have. We dealt with constants when we were talking about circular motion. Okay? And so a lot of times you'll just string units together to make it all cancel out. But joules per degree Celsius, so what that basically means is that's the amount of energy that would be required for every degree Celsius increase in energy. And so it's similar to specific heat in a way, but it's a way of also representing, the disorder of the system. So what tools do we have? What's our formula?
We have the change in G is equal to H minus
Yep.
T.
Good. Delta G is equal to H, and sometimes you'll see this as delta H, change in enthalpy, so that you could do that the system changed this amount in total heat of the system. But notice here, and so also we have another tool that says a negative delta G is spontaneous, right?
Mm-hmm.
So whenever delta G is negative, you have a spontaneous process. And so now, what do we want? Oh, that's EOUS. I left off a U. What do we want?
Is it spontaneous?
Yeah, we want to know is it spontaneous, and in order to get that, we need to calculate delta G, right? So delta G is equal to enthalpy, which is 457.5 joules, minus temperature, which is 55.4 degrees Celsius, yep, times delta S, which is 4.37, yep, joules per degree Celsius. And so degree Celsius is going to cancel here, degree Celsius and per degree Celsius, and we'll end up with a delta G that is equal to 215, and that's with 3 significant figures?
Yeah.
Good.
That's what I got.
215 joules. Is delta G negative? No, it is not. So is this process spontaneous? No, it is not. So whatever this reaction is, it is not a spontaneous reaction. And what does that mean in terms of what we've been talking about so far?
Have to add heat to it.
You would need to add energy in order to make that happen. Yep, you need to, well, heat is a form of energy. Heat is kind of wasted energy, if you will.
Okay.
And so, yeah, so delta G for this, 215 joules, this is not a spontaneous reaction. Make sense? Does that mean it can't happen? No, it just means that in order for it to happen, you have to input energy. So if this represented something that is necessary for life to happen, it would just require energy to make that work. Which is why you have to, consume, you have to keep eating every day, right? You need to provide the energy necessary to fuel these non-spontaneous reactions. All right, next problem. What is the Gibbs free energy for a system? Oh, that should say that. Sorry, not than. That has an internal energy of 27.5 joules, a volume of 22.3 liters, a pressure of 1.25 atmospheres, and a change in entropy of 255 joules per degree Celsius at 75.3 degrees Celsius. There's a lot here. So it should clue you in when we get to the tool portion. We need a tool that's got a lot of information, or the problem's giving us unnecessary information, which is possible, but we'll see what we're given. So that has an internal energy. What do we use to represent internal energy? U. U is equal to 27.5 joules. We have that volume is equal to 22.3 liters. We have that pressure is equal to 1.25 atmospheres. We have temperature is equal to 75.3 degrees Celsius. And finally, we have delta S, change in entropy, is equal to 255 joules per degree Celsius. All right. Now, let's start thinking about what tools we might use and see if we have any information we don't need. What's a tool that we have? Remember we expanded our equation for delta G. So we have delta G is equal to U, right? Plus P times V minus T delta S. Do you remember expanding it out? Plugging in U plus PV in for enthalpy. And so what do we actually want? What is the problem asking us for? Asking us to calculate.
Gibbs free energy.
Yeah. what is the delta G? And so that's nice. It's already set up the way we want it to be. So we're just going to plug in what we know. 27.5 joules. And then plus pressure, which is 1.25 atmospheres. Times volume, which is 22.3 liters. And then minus temperature, 75.3 degrees Celsius, times the change in entropy, which we had as 255 joules.
Per degree Celsius.
255 joules per degree Celsius. Now, it's a bit beyond the realm of what we do here to explain the relationship between atmospheres times liters and joules, but suffice it to say that when you multiply these together, we get something equivalent to joules. Okay? So a bit beyond what we're doing here, and it gets into some complex things. But for these problems, just consider atmosphere times liters to be equivalent to a joule.
So you want the answer?
I do.
Okay.
Yeah.
I got negative 19,146.125.
Okay. So negative. So we want it in three significant figures, right?
Negative 191,000.
Negative 191,000.
19,100.
19,100.
Yeah.
Negative 19,100 joules. You get that as well, Daniel? Okay, so when delta G is negative, is that spontaneous?
Yes.
Yes, it is. So would this be spontaneous?
Yes.
Yes, it would. Okay. Now I know the problem didn't ask us for that, whether or not it was spontaneous, but it's helpful nonetheless. Okay, helpful nonetheless. All right, any questions on this one? We've got one more problem that we'll do together, and then we'll talk a little bit about data that you collected for the previous lab, so that we can get those data to Joey. Do you want to go by Joey? Okay. That's just what you wrote in your email, so that will help me remember your name, and I won't be tempted to call you Jacob. I've told you about my temptation to call you Jacob, right? Yeah. The whole father-son relationship, it's confusing for me. All right. So if the Gibbs free energy of a system is 4.56 kilojoules, what is the change in entropy at 65.3 degrees Celsius if the enthalpy is 789.3 joules? All right, so our first question, what do we have or what are we given? All right, so start giving me what we have. We know delta G, right?
Delta G is
4.56 kilojoules. And then keep in mind that the root or the prefix kilo means what?
1,000.
Means 1,000 times the base. So this would be equal to 4,560 joules.
That's what I was messing up on.
Yeah, and that's a hard thing to be mindful of, is what the actual units are, because sometimes they're, have those prefixes and sometimes they don't.
Yeah.
What else are we given? We're given that H, or the change in enthalpy, is equal to 789.3 joules. And then we're given we are not given delta S. We're given temperature.
Yeah.
Is equal to 65.3 degrees Celsius. I keep wanting to think I was writing down change in entropy, and I was like, oh, I messed up the units. It should be joules per degree Celsius, but it's temperature. All right, so what tools do we have? We've used this tool before in the first problem that we did. Do we have a tool that has delta G, H, and T in it? Sure do. We've got delta G is equal to H minus T delta S, right? And we want to rearrange this to solve for delta S. So first thing we'll do, we'll add T delta S to both sides. And so we get delta G plus T delta S is equal to H. Now we'll subtract delta G away from both sides. And we'll get T delta S is equal to H minus delta G. And then we'll divide T away from both sides. You all okay with those algebraic steps? Okay. And ultimately our tool would be that delta S is equal to H minus delta G over T. Good. Now, we already manipulated our formula to get what we want. We've already, in essence, answered this question. But what do we want? We want delta S. So delta S is equal to H, which is 789.3 joules. Minus 4,560 joules. Good. Using the right form of it too.
Over T, which is 65.3 degrees.
Over temperature, which is 65.3 degrees Celsius. So we got to subtract those first, and then we'll get our units will be in joules per degree Celsius, which is excellent because those are our units that we've been demonstrating so far for entropy. 57.7. Negative 57.7. How'd we get negative? Because this number is bigger than this one.
Yeah, the 4,560.
Oh, this is 0.3.
Oh.
I was looking at it as 7,893. So negative 57.7 joules per degree Celsius. So now let's think about this. And I know this problem doesn't necessarily ask for this, but we're going to think about this nonetheless. If delta S is negative, what does that mean? Are you becoming less disordered or more disordered? Keeping in mind that delta S it's a change in entropy, which means your entropy is decreasing. It's negative, right? So your entropy is actually decreasing. Does that make sense? So if your entropy is decreasing, are you becoming more or less ordered? If your entropy is decreasing. More ordered. Yep, so this process, this is becoming more ordered, less random, more ordered. Since delta S is negative, we are decreasing in entropy, which means we're becoming more ordered and less random, which means that this is probably very unlikely a spontaneous reaction. But we already knew that. Why?
Because negative 57.7.
Well, not because of that. We already knew that even prior to doing the problem that it wasn't a spontaneous reaction. Because our Gibbs free energy is positive. And not just positive, really positive, right? 4,560 joules. So our Gibbs free energy is really positive. So this is certainly not a spontaneous process. Which makes sense when we look at that it decreases in entropy, meaning it's becoming less random, more ordered. It makes sense why it would not be a spontaneous process, right? But oftentimes one still essential and necessary for life. All right. So the nice thing about this formula here, this delta G equals H minus T delta S, it's simple enough, but it also can be manipulated quite a bit.
You can fill in for H.
Right, we could solve for H, and if we were solving for H, this would actually be a very simple one. We would just add T delta S to both sides. So you'd get H is equal to delta G plus T delta S. You can manipulate it to solve for T, and you would do that the same way we solve for delta S, except for you would have T is equal to H minus delta G divided by delta S, but ultimately it would be manipulated the same way. Bit more complex algebraic manipulation, but can still be manipulated that way. Our other more expanded form of delta G is a bit more complex, right? You've got U plus P times V, then minus T delta S. So you get a more complex problem to change algebraically.
So even if you get like the last question, if you get all of that work, you don't have to use all of it. You can just do this.
Well, the problem with that is so on the previous problem, it didn't give you enthalpy. It actually gave you what you needed to solve for enthalpy, but it did not give you enthalpy, the total heat of the system.
Okay.
You actually had to use what it gave you, the internal energy of the system and the pressure and volume to calculate enthalpy. Yeah. So I told, maybe I didn't tell you, but last week we talked that we won't actually meet for class next week. Instead, we will. I'll record a lecture like this and send you all the link on YouTube, like this one is, and then this week, and this is where I don't think I did mention it to you, but this week, in addition to sending you a homework assignment that will cover lesson 12, I will send you a quiz that will cover lessons 10 through 12, 10, 11, and 12. Now the quizzes will be assessed the same way homework will. You know, you won't be graded down for not doing things correctly, and you'll only be graded down for not completing it. Okay, so this week you'll have a bit more work because you have a homework assignment and a quiz assignment that will cover the first, but it should be okay. And you know, and in this, the nice thing about thermodynamics is the equations are simple. You know, the concepts are a bit more complex, right? So, you know, a bit more difficult to wrap your heads around, but the actual equations tend to be fairly simple, and so the calculations tend to be fairly simple. All right. Any questions about these materials or any of it? So if you were to sum up the second law of thermodynamics, how would you do it?
Randomness.
Okay, so randomness is entropy. So it's the second law of thermodynamics. You need a bit more than just randomness, but you need to say what? Yeah. Yeah, the randomness of the universe is always increasing. Yeah. So essentially, you know, if you've ever heard the idea that our universe is actually moving towards a heat death, right? Have you ever heard that? Or somebody talking about that the sun is destined for a heat death? What that basically is where it increases in entropy and reaches, in some ways, maximum entropy. So that's the idea, that the universe, the disorder or the entropy of the universe is always increasing. And so because of that, at some point the universe will kind of reach maximum entropy, which would be heat death, which would basically even atoms, like individual atoms, have a great deal of order. So in order for that to happen, you would need to break apart even individual atoms into their individual pieces and allow them to be strewn freely. So, because even in putting together a single atom, you know, an atom's made up of protons and neutrons and electrons, and again, this is in chemistry class, so you're not going to be assessed on this. But there are only certain ways in which you can orient those materials and make the atom. Okay, so even an individual atom has a high level of order. So, all right. So let me, yes, I would love to keep these. I would love to